Okay, so there we go. Um, Standard, just kind of our announcements here. This week is Lab 8, where you're kind of preparing for the input modeling part of your final project. And so I will give you, I'm in Lab 8, I give you a bunch of data sets, basically ask you to fit them. So practice a lot of the things that we're talking about here. So we talked about data collection last time, but we're going to start actually talking about fitting, choosing distributions and fitting them this time. And you'll talk about that in Lab 8 and how Arena has some tools to help with that. So that is, this week. And then next week, we've got an open lab, which basically means there's no lab, but instead you can use that time to work with your group to work on gathering data or fitting data or writing this input modeling report, which will be due basically in place of a lab report for that week. Then after that, there's labs 9 and 10. They're on our regular schedule. And then we have, I think, 2 open weeks that we leave open. Don't bother you with labs. So you have plenty of time to keep working on your final project. So the final project, information's online. There's general description. There's the structure of the report, which is 4 pages long with specific sections. There's the presentation information, 10 minutes long. Basic idea, pick a system that you would like to model from the real world. If you're needing help coming up with ideas, recommend taking a look at chapter 9 of your textbook and exercises 1 through 5. There's some good ideas there, just to get you thinking. You don't have to pick from one of those. This is a group project, so you have to pick these teams of nominally 4, but maybe groups of 3. But if you choose a group of 3, I might end up having to augment members of your group just to make the numbers work out. So preferably, like everybody to shoot for teams of 4. That'll make things easier for me, and it'll generally make things better in the end when we do the peer reviews and things like that. So the first deliverable is actually this week, technically due Friday to Canvas, and it's just a list of your team members. Several of you have already submitted this. You've already kind of declared your teams, and I've started to put you into your groups. Every member has to submit this thing, even if another member has already submitted it. So this is one of those ones where I want to make sure that everybody agrees on who's in their group. So that's why everybody has to submit it. If you're having trouble finding members, of course, if you go to the lab period, come to class, that's one option. The other thing is I've provided this Google Drive spreadsheet where you can put your name if you're looking for a team member or if you have an incomplete team looking to add one. And then just keep going back to that sheet and reaching out to people. Or you can post in Canvas discussions, post on Slack, etc. So if you're having trouble, try to reach out to me ahead of time so that I can help you facilitate that. But hopefully you'll be able to use these resources to help find team members. Other things, ICAs, as usual. We've got this G3 one that's coming up, H, J1, J3, and L, and that's all of the normal ICAs. And then we'll have the last ICA will be a final exam review ICA, just like the midterm exam review ICA. There's a homework. I still haven't released it yet. I didn't have a chance. I had some other my own due dates yesterday that fought for time for me finishing this assignment, but I will have this posted before the next lecture. And that's when it's technically supposed to be released anyway. And then you'll have about 2 weeks to work on this one. It's another one. It's basically 2 problems. It's kind of an extended chi-squared analysis with a hypothetical distribution that is not a uniform, and then there's a power analysis. And so that's how the 2 things will be there. So one of them should feel kind of like review from 380, and then the other one, I think the power analysis will be new. And then, keep thinking about the final projects. Again, form those teams ASAP by Friday. Thanks to those who've already submitted those. By distributing that work out over the week, it makes it a lot easier for me. And then that's pretty much it. So input modeling report is your next week's lab report. So lab 8's lab report due this upcoming Sunday is lab 8. Then the Sunday after that, that's your input modeling report. So this week, do lab 8 and form your teams. Next week, start working on your input modeling report. And the format for that is posted online. All right, so any questions about any of that? Also, and I'm not trying to be a bad guy here in any way, but I got, every instructor in this building got an email from the director, CB, the kind of school that owns this building, about skateboards and things. And apparently, so this building is it's one of the nicer buildings on campus, one of the newer buildings. They also bring in a lot of funders and things like that. And the foundation and the president's office, who sort of, work with the funders, get really upset when they see like scuff marks on the walls and things like that. So we have been told to tell you guys to try to abide by the no wheels policies. You notice there'll be more signage on the walls. And then they also say in about 2 weeks, they're going to step up enforcement. And so I don't know what that means. I don't know if that means that we'll have the Gestapo come in here and take your boards and put them somewhere else or write tickets or anything like that. But it does mean that apparently something will happen in the next sort of 2 weeks and all that. So I know it's inconvenient. I don't know why they don't have options inside the building that make it a little easier for you to lock up these things. But they do claim that they feel very confident about the safety. So I guess part of the enforcement will also be patrolling areas where you might things might get stolen. But anyways, not something I want to take a lot of time to talk about, but I need to do my due diligence and tell you that I've been told to tell you that they're really upset about the devices, scooters and otherwise. And so I'm supposed to pass on the word that they're going to be stepping up enforcement soon. So keep that in mind. Okay, so getting back on to the other things. So we've been talking about input modeling. Hopefully everybody feels comfortable with this idea that we're picking random variables or processes as the inputs to simulation models. We can have one simulation model like this very simple system down here. Part A arrives at the system, goes to the drilling center and leaves. But if we change the arrival distribution or the service distribution, here you get very different outputs. And that's hopefully something you saw in part 1 of lab 6. Similarly, when you take like 470, you learn about nodes and queuing networks, and you learn that each node, you can have the exact same network, but what if you call a node, an MM1 or a DM1 or a variety of other things, all you're basically doing is changing the input models on that node, and it totally changes the structure of the system. So drawing the system is one thing, but then choosing the models that go into the system is just as important. And that's what we've been talking about here. So for queuing models, the big input models are like inter-arrival times and service times. For supply chain models, there'll be demand distributions and lead times. For reliability problems, there'll be our failure times. And of course, you can combine these things. There can be queuing systems that have machines that fail, in which case you have to import these failure times. So these are sort of the 5 major input models that we mix and match from as we build these networks and these simulations. And then we choose distributions that hopefully model the real world. If the distributions of the input models don't match the real world, no matter how realistic your system looks on a diagram, you'll get outputs which will not be valid. So the easy part to this whole process, as we say, is hypothesis testing. So if I come up with this hypothesis, that this is what an input model should look like, and I have data from the real world, I can test whether this hypothesis matches these data or vice versa. That's like, the chi-squared, ks, etc. The harder part is coming up with what's up top here to begin with. So looking at data, how do I get that up there? And that's what we're talking about in this sort of section. So we talked about how we collect that data last time. So the next step is identifying a distribution to represent the process. And then what we'll talk about next time is choosing the parameters for that distribution and then evaluating how well things fit. So, last time we were talking about when you collect data, and I said that we were going to embellish this example I had where the times it takes to move through a metal detector were kind of bimodal. So let's actually see how we build that system. And they'll give you hopefully an idea of what I mean about choosing the input models is sort of like choosing the structure of input models and how choices of input models can sometimes feed back on your diagram and cause you to iterate on the diagram. So we've got this, it's the same thing I introduced last time, a metal detector. So we've got people or entities, the resource of the metal detector, the activities or the time it takes to pass through the metal detector. I'm just going to float back here and make sure I didn't miss any questions online. Okay. And so the first thing I do inside Arena is I go into that data section, data entry or whatever it's called on the left-hand side, and I go into the entity data module and the resource data module, and I configure that. So I say I'm going to create an entity in the spreadsheet view down at the bottom called people, and I'm going to have a picture person just for visualization's sake. I create a resource called metal detector with a fixed capacity of 1. And so that's good. So now then I have to then draw a flow chart. Well, I'm going to go and grab a create module and configure it so that people are the things that are arriving via the create module. And let's just say I choose an exponential inter-arrival time for them. I need to draw a process that uses the metal detector resource. So it's going to seize a metal detector resource, delay a person, and then release the resource. And the delay type is what we're choosing the input model for. And then a dispose block to collect the people after the detector. And what that looks like is this. So hopefully after lab 6 and so on, you feel comfortable up to this point. Is there anybody who has questions about any of this point, this idea that this is the create block, that's a process block that's been configured to use a metal detector of capacity 1, and then everybody's collected at this dispose? Does that feel comfortable so far? Like you could draw that out? Okay, good. All right. Questions online? Okay. So again, so we're just assuming we know the inter-arrival distribution, assuming it's exponential. It won't always be exponential, but for this point, we're not focusing on that. We're focusing on the service time, how long it takes to actually walk through the metal detector. And from last time I said, we looked at 1,000 people that walked through the metal detector, and we found that their mean was roughly equal to the standard deviation. So the sample mean was roughly equal to the sample standard deviation, which is about 30 seconds. And so without even looking at the data, I could say, well, you know what? There is one continuous distribution whose, and there's not necessarily only one, but there is a continuous distribution that I know of whose mean is equal to its standard deviation. And that's the exponential. So I might just assume that I need an exponential with mean 30. So if I think about it, like this is a hypothetical exponential with mean 30, and this is sort of hypothetical data that would be underneath it, that might sound good until you look at what you're saying here, and this would suggest that a significant number of people would take 100 seconds to walk through that metal detector. And there's even be some that would take even longer than that. And it seems weird that it would take 3 minutes to walk through a metal detector, just that. So it feels like this is not really, that I'm missing something here. So I should then take a histogram of my data. In fact, you should always look at your data, look at the shape of your data. So, so this histogram here represents, I took the time, the service time, how long it took each person to walk through the metal detector, and I created little bins, and I counted up how many people took 5 seconds or less, how many people took between 5 seconds and 10 seconds, and so on and so forth. And of those 1,000 people, each bin got a different number of people that would fell into that category. And I got, now this bimodal distribution where some of the individuals spent mainly a quick time going through the metal detector. Other individuals took a longer time, nobody in between. So when I look at that, it tells me, well, for one, this is not exponential. I can't just put an exponential in here. It would be a terrible fit if I were to put an exponential in Arena here. So I could say like, well, let's just find the Arena distribution that looks this way. But there is no already defined Arena distribution that looks like this. So I could take the inverse CDF approach. I could turn this into a sample cumulative distribution function. I could load it up into the cont function to create a continuous distribution out of it. And that would be one way to do it. And that would allow me to maintain my flowchart as it is. But rather than that should sort of be the last, your last resort. When I look at this, this really tells me that I'm missing system structure, that there is a structure that is dividing people into two groups. One of the groups, which is over here, the other group that is here. And if I modify my flow chart to include that division process and those two separate things, then it's going to be much easier for me to model the thing on the left separately from the thing on the right. And those are things that actually will be in ARENA. So I look at my histogram, I look at my CDF. The CDF has a big flat spot in between. That corresponds to this empty spot here. So it's got two rising areas that also tell me that it's a bimodal distribution. And if I split them, so if I say, let's take everybody who's under 50 seconds and put them in one distribution, and everybody that's over 50 seconds and put them in another distribution, those two new distributions that I created, these actually look like things that I recognize, or they look kind of like things that I recognize. This looks maybe like an exponential. This looks maybe like a normal distribution or a triangular. It looks like something that ARENA can implement simply. And that's good. That's something that I would prefer. So what I'm going to do is I'm actually going to now break my one input model, service time, into three input models. I have a long passage time input model. Those are maybe the individuals who triggered the detector and required extra screening. A short passage time distribution. Those are the ones who walked through the detector, didn't trigger it, and could go along their way. And then a probability of who's in which group. So probability of triggering the detector. So I now need to go to my flow chart and I need to add a decision block for this probability. And I need to make sure I have two pathways, one for the long passage time pathway, the other for the short passage time pathway. So I go back into ARENA, I go to flowchart, I create a two-way by chance decide module, and that probability is going to go in there as that chance. And I create a separate process with a seize delay release on that metal detector resource, and then another dispose. And so what that looks like is this thing here. Everybody arrives in the same place. Those who are the unlucky ones who are going to trigger detection, they are going to go through a process of the metal detector and getting checked. It's a little bit unrealistic because this process is going to seize the metal detector for that whole time. But for now, we're just going to be okay with that. And then they get disposed. Otherwise, most people go down through the bottom one here. They don't flag the metal detector, and they'll just go through and be delayed by however long it takes to just walk through a metal detector without getting stopped. So there are questions about this modification, how looking at the service time data told me that even though in my head, it's arrive to the building, go to the metal detector, go into the building, looking at the service time data told me I needed more. And so that's what means I had to arrive to the building, get sorted in to the group that's going to take longer or be shorter. And notice this doesn't quite match what happens in reality. This is almost like, did you decide to wear a piece of metal on you that you forgot to take off? So this two-way by chance happens before the metal detector. You might in your head think I passed through the metal detector and then the two-way by chance happens. But the way I've coded it here, I've kind of flipped those. So it's almost like, are you someone who takes long in the metal detector, or are you someone who takes short in the metal detector? So there are questions about this new flow chart and how it is a response to the bimodal distribution. Questions online too. Okay. So that's great. So now I can start, I basically can drop in a service time distribution. Let's say I fit a normal distribution to the long one and an exponential distribution to the short one. And then my probability here, well, if I think about it, I can go back and look at this split and I can say there are about 600 people in this group that are less than 55 seconds. And there are about 400 people in this group that are greater than 55 seconds. So that gives me a probability. So the probability of being in the short group is 60%. The probability of being in the long group is 40%. So that tells me that this should be about a 40% chance of detection. This will be normal, this will be exponential. Now I can play around with different probabilities of detection and I get different outputs like this. So this is looking at how long it takes. This is me actually doing that simulation. And I'm showing you how the distribution of the time in the system changes as the metal detector probability detection changes. So like in this case, this is people who are frequently go through the metal detectors. They know to take off their shoes and whatever, they get through very quickly. So this is like a 10% chance. And you can see that this basically looks like an exponential with just some ugly outliers, but pretty much just an exponential. On this side, this is like a population where they're always new to the building. It's always flagging the metal detector. Maybe they're a little bit older, and it's a new system, and so on and so forth. And here, it's pretty much almost just this normal distribution, and the outliers are actually the little exponentials. And what we actually saw in the data is closer to something that looks like this, where you've got these two strong bimodal peaks. So that's just me experimenting with, and now you could say, well, like, let's say this is our baseline system. Well, if I want to change the average time, I can play with this probability of detection and look at the averages that come out of my simulation. And so if I have a performance target, like I want the average performance to be 20 seconds, then by playing with this simulation, I can figure out what detection probability corresponds to a 20-second average. And that will tell me how much extra effort I need to do when people are coming into the building to say, hey, make sure you take off your belts or whatever. And so, that's why, like, when you're at the airport, when they're really running behind, then they're really yelling at you to follow the rules as you come in. Whereas if things are pretty slow, then it's okay if someone sort of, doesn't take things out and all of those things, because they're kind of in a situation where they don't need to worry, that their averages are not that bad. So this kind of shows you, how you can choose to adjust your resources to hit the targets you want. So any questions about this scenario, or this idea? Okay. All right, so let's think about another situation. Let's say you look at that service time distribution, and it looks like this thing over here. So this is the histogram. It's got a bunch of peaks, not just two. And if you look at its cumulative distribution function, it's got a bunch of these little steps. And so it's got a bunch of rising steps here. Now, a lot of times when we see rising steps in a CDF or a bunch of peaks in a histogram, we think it might be discrete data, but we know that this isn't discrete data just by the physicality of the service time. Like, it doesn't make sense that it would be discrete data here. Now I can take off this early portion and separate out those who were like less than 20 seconds or more than 20 seconds. And that kind of looks like an exponential I could probably fit. About 580 people fit into this group, but the other 420 still have got a bunch of different peaks. Now, does anybody have any thoughts about, like, so this indicates to me that I probably need to change my model of the system, my flow chart, to reflect something else that's going on. Does anybody have any ideas of what else might be going on in the process, in the logic, that could generate these strong extra peaks? Any thoughts based on your own experience of walking through metal detectors and so on? Yeah. So what's one hypothesis? Maybe this is randomly chosen for extra search. But if it was just random choice for extra search, then it seems to me like I might have more of the bimodal. Like, I'd have those who, or maybe trimodal, because I might have those who are randomly chosen for extra search but don't take that much time, those who are flagged for search by the metal detector and take a lot of time, and then everybody else. And so maybe there's but here I've got like a bunch of extra modes. So what it seems like I need something else more complex to generate that. Yeah. So that's kind of an interesting question. Is it like, is there a feedback between the number of individuals who've gotten flagged downstream and how they slow things up kind of upstream? And that probably can happen. That isn't necessarily we'd have to sort of say, why would we expect there to create these kind of, like, I mean, when I look at this histogram, this is saying that there's a group of people that take about 4 seconds to go through. And it's like these separate discrete groups where this group takes, I don't know, 60 seconds. This group takes an average of 120. This one takes an average of 180. This one's 240. So it's this discrete grouping. They're all separated by 60, where I feel like if there were some other things like that happening, it would be more like there'd be an exponential that'd be kind of wibled out, like it'd be stretched out in some funny way. But I have to think of what process could create discrete groups. Well, I mean, but so that's kind of pushing it down. Because the way I could just be that there's all of the fast people arrive at once, and all of the, or for some reason there's fast people, there's slightly slower people, there's even slower people, there's even slower people. But why would be separated by just 60 seconds? Like, it just seems like there's something else there. Yeah. Well, that could be that, like, that there could be that, like, these are individuals. This is families of 2, families of 3, families of 4. And at that point, we're like, well, maybe every time you add a family member, you add 60 seconds. And it sounds weird that, like, a family member would add exactly 60 seconds. So these are all great ideas. And before, I don't want to say anything wrong, we could implement all of these ideas and we'll run our simulation. And if our sim did not generate something that looked, I'll go back to like this, then we would reject our hypothesis. So we would say, yeah, it might be these different family types, but then we find that it's really unlikely that I could come up with a distribution of families that would give me exactly this, and so on and so forth. And so I could go and investigate that. So what I did when I generated this model is I thought about people who returned to the metal detector and had to get scanned again and had the possibility of getting flagged yet again. So when I zoom in on these peaks, I see that if I look at a peak at average of 60 and I look at a peak at average around 180, they both look like roughly the same distribution, like something looks kind of normal or triangular, but just shifted up. This one has fewer individuals in it, like it's only got 45 individuals versus 253, so that's why it looks kind of ugly, but the shape is roughly the same. So to me, when I look at this, I think, well, this is like a single process that some people go through once, other people go through twice, other people go through 3 times. And that to me suggested, well, maybe that I can actually get that by saying people arrive, they go through a metal detector. If they don't get a detection, they leave. So now I've got the decide block after the metal detector. But if they did get a detection, they get extra checking. So that's, pat downs or whatever. So that's a different resource. So we've got the metal detector resource here and the agent who's doing the pat downs here. And then they go back through the metal detector just to see if, that fixed it. And it may be that they get flagged again, get another pat down and go back through, and so on and so forth. And if I do that, then I actually get this distribution here. So what we're seeing here appears to be, there's like a roughly, each one of these kind of normal shaped peaks represents that kind of pat down time. And so it's kind of like it takes, the reason there's a gap here is it very rarely takes less than 50 seconds to pat someone down. It almost never takes more than 80 seconds to pat someone down. And it often takes about 60 seconds. So what you're seeing here is you're seeing individuals that go straight through the metal detector, individuals that get patted down once, individuals that get patted down twice, 3 times, 4 times, and so on. So that's at least how I generated these data, is by having individuals being able to recycle through the system. And that recycling is why we saw the same distribution kind of show up in copies and multiple modes down the line. Now, that's not the most realistic model. It should be that every time you get checked, it should probably change the probability of detection to be lower. And we could build that into this model where we could keep track of how many times they've gone through, and based on that, change the probability so that it goes down as the number of checks goes up. And then we'd have to figure out what that relationship is in the real world. And that would change this distribution so that maybe it didn't look like exactly the same hump at every single mode. But just trying to use that as a simple example of how we can try to use shapes of distributions to suggest to us things that might be going on. And when I see consistent gaps like this, it tells me in my head, is there a process that's being repeatedly used in a system? And if I can come up with that, then maybe if I can figure out how to cycle things through that process over and over again, I can come up with an explanation for where this comes from. And maybe it just takes me like, when I gathered my data, I just forgot about that. And now that I looked at these data, I go back to the source and I see that people are cycling through. And once I account for them cycling, I can explain this. And now I know what to build in my system. All right, so are there questions about that general idea of trying to help the data guide your flowchart decisions as well? Questions online? Okay. Great. So that's all about the flowchart. So today, it's a lot about then, once we feel good about our flowcharts, well, we're going to talk about histograms, and that helps us get to the flowcharts. But once we feel good about our flowcharts, then how do we at least get in the ballpark of the right family of distributions for the data that we're looking at, for an interarrival time, for service time, and so on. And a big central part of that is the histogram. So, so if we think about histograms here, for continuous data, this gives us kind of an approximation to what the probability density function might look like. It's a chunky approximation to the probability density function. Those of you who go on and take some data science courses will learn about something called kernel density estimation. That is a smoother version of a histogram that tries to smooth out those humps so you get a better idea of the probability density distribution function. For discrete data, this is also kind of a histogram is sort of an approximation, but it's a little bit closer to approximation because the probability mass function is already kind of chunky. And so for discrete data, the histogram is really meant to approximate the probabilities of each outcome. So keeping all that in mind, we have to figure out what are some guidelines for choosing the bin sizes, how big each bin is, or how many intervals that you have. And so this is largely an art more than a science, but a good choice of the number of bins and the size of bins is going to depend on the number of observations you have, as well as how variable the data are. So for continuous data or large numbers of discrete data, large numbers like counts where the average is 10 or higher, then you can choose you want to choose the number of bins. Usually you start out with the square root of the sample size. So 100 samples, 10 bins, and so on. Now for discrete data, unless it's a really, really large number of outcomes, you don't do this game. You just bin every outcome separately. So on your homework that I'll release in hopefully tomorrow, but definitely before the next lecture, in that homework, you're going to be looking at discrete data where you definitely will have to bin every outcome. So it's like count data where you're going to have to bin, how many times did count 1 come up, count 2 come up, and 3 on. You don't initially group them together. You might group them together when you do a chi-square test or something later, but if you're doing a histogram, then you bin every outcome separately. You don't group them together. And I'll show you what I mean by that here in a second. So here's continuous data. And so these are the same data, but I just I've binned them with different bin sizes. So up here, I've chosen a very small bin size. And notice that the frequencies don't get very high. The highest frequency is 6. There's 6 samples that fall into this bin of from 12 to 13. But most of them are down here with only 1 observation or 2 inside those bins. That's a bad size because at the point where, like, the whole point of a histogram is to change data encoded in sort of time, sort of like samples, numbers of samples, to space. Like, you want to be able to get an idea of shape out. But once you've got only like one observation in every bin, the bins are just your observations. And so you may as well have just plotted them around a real number line, because you're not going to be able to see what the shape is. But you can go too far. Like here, you've gotten only 3 bins here. And this, it's hard to tell the difference between this and like a uniform distribution. If I only went down to 2 bins, it would look almost totally flat. And then every data distribution, if you only choose 1 bin, is going to look uniform, because you lose all information about how things are distributed inside the bin. So this one down here looks kind of perfect to me, because every bin has got a good representation. It's got clear shape. So now I can definitely tell that there's a few outcomes in the middle that are much more prominent than the outcomes on the side. So that tells me that this is probably a good choice. But, like, I'm not saying there is one perfect choice. There are probably several choices that are going to give you this idea here. And you have to kind of play around with bin sizes to find it. And it's going to be variable. So not every time you take 1,000 samples, you'll use 100 or 50 or whatever bin. You're going to have to play with that based on the particular data that you have. So to me, this is the best choice, but you kind of have to look at it to see it. Now, if we instead looked at discrete data, like these data here, so by discrete data, I mean, these are the outcomes, arrivals per period, 0, 1, all the way up through 11, and frequency. So 0 of the periods had 12 arrivals. Or sorry, I guess I'm going to say that there was 12 periods that had 0 arrivals. There were 10 periods that had 1 arrival, 19 periods that had 2 arrivals, and so on. And so you might think, well, I might want to group together 10 and 11 or whatever, but when they're discrete outcomes, I really want to see the probability. I want to get an estimate of the probability per outcome. So with this discrete data, the histograms are going to, the bins are just going to be set by the outcomes themselves. And if you can't see a shape, there might not be a shape there, but at least you can estimate the probability per outcome. And that in itself will be the thing that you'll end up putting into ARENA with the disk function. So can anybody guess that what this distribution might be? It's sort of a skewed distribution. It kind of starts low, it kind of peaks up at its mean, and then has a long tail off this way, and apparently describes count data. What's a common count distribution of the discrete distributions? Chi-squared is a test for count data, but that's good. I definitely want everybody to have that. When you think count, I want you to first think on statistical. If I say count test, you should think chi-squared. But if I say count distribution, you should think this distribution. So what distribution is like the count distribution? There are a bunch of distributions that count things, but it's like the generic, like if you got no other distribution, this is a distribution you typically use to represent counts of events. Poisson. So yeah, that's what I would say. This is what a Poisson distribution looks like. With a high number of counts, it gets symmetric because of the central limit theorem. Every count distribution gets symmetric because of the central limit theorem with high averages. But with low averages, it looks kind of asymmetric, where it typically ramps up and then comes back down. So that's a Poisson. All right, so once you once you've looked at your histogram, so here I kind of guessed that it was Poisson, and here I could guess something else. Ideally, I would like to fit a distribution that ARENA has available to it. It's just easier on me. So if you go into the expression builder in ARENA, so anywhere where there's an expression that you can type something in, you right click and you go down to build expression, this thing will pop up. And it has a category of random distributions. And these are all the distributions that if you click on them, it pops up parameters and you put those in and you're done. And so ideally, you've got, this is kind of a large enough vocabulary that allows you to cover most continuous and discrete distributions that you'll run into. So hopefully you find one of these that works well for you. So, but when you choose them, you should think about, the physical properties, for example, discrete or continuous. So even if the histogram looks like it matches up, if it's a discrete distribution and these are continuous data, it's probably a bad choice. Is it bounded? That's kind of a big thing there. We're going to learn that there's this input modeling tool that you'll learn how to use in Lab 8 in Arena, and it will often fit bounded continuous distributions like the beta distribution, beta. Up here, the beta distribution's got a key feature that it's bounded from below and above, but it's very flexible in between its bounds. Now, if you have continuous data that are bounded from below and above, beta is great. But if it just happens to fit a beta distribution, but you know it's possible for you to have outcomes that are well outside of the outcomes that you happen to sample this time around, don't choose a beta distribution, because Arena will not generate anything outside the range of the beta distribution. So that's kind of the big thing. Discrete or continuous, bounded. Are there other features you know of? Is it memoryless? That suggests maybe it's an exponential or a geometric if it's discrete. Is it an additive process? Well, then maybe it should look like something more like a normal distribution or some relative of a normal distribution. Is it correlated with other processes in the system? Is the service time related to a service time upstream of that? So is a downstream process related to some already drawn random variable upstream? And you want to make sure those are there. Those are really important things. And then, of course, then the shape of the histogram. Those things together should guide your choice. So our goal is not to find a perfect distribution, it's to find a good approximation for a complicated process. You will always find the distributions you choose will always only explain a fraction of the variance in your data, but that's okay, because there's going to be some variance that you just leave out because it would make the model too complicated and wouldn't give you a lot more ability to analyze the system. So frequently encountered ones, and these are ones that you often see in Arena as well: exponential normal Poisson, uniform beta triangular gamma Weibel. These are, and then again, the other ones that you already see in Arena. If you look at lecture D2, I've given you tables of these things. If you look at chapter 5, Banks et al. Also give their kind of version of the greatest hits that you should sort of be familiar with. So that's basically the, how selecting a family. Think about the context, think about the shape. Don't look for perfection, and try to stick with, at least at first, the distributions that are easy to implement. And then there are, worst case scenarios that we'll talk about, ways to implement, if nothing fits in Arena, what can you do? We do have options for that, but they really should be the worst case options. So, and just see examples of this, and you'll see more of this in Lab 8. Discrete or continuous. This over here is discrete. This is continuous. I'm looking at a histogram of data. Discrete histograms have big gaps in between them, and they have got no side lobes. So if you zoom in on a particular outcome, there's no outcomes that are kind of close to it. It's like here, I've only got 4 things that could happen. Contrast that with a continuous distribution. Here, regardless of what my bin size is, there's no gaps in these outcomes here. So clearly there's intervals that are represented here. So that's kind of if I look at a histogram, you should be able to tell that's probably discrete and that's almost definitely continuous. So any questions about this distinction? Discrete on the left, continuous on the right. Notice that the outcomes here that are discrete, they don't necessarily land on integers. It's not where the outcomes land, it's how many of them there are. Okay. I can also look at sample CDFs, empirical CDFs. And so the sample CDF here, this is the same data, but I've now sorted the outcomes and I've plotted them against their rank, and I get these stair steps. And when you see steps in a CDF, that indicates discrete. So, because every vertical step is an outcome, and every flat portion is a gap between outcomes. If in a CDF instead, it's a smooth rise, then that tells me that every single outcome in this smooth rise is represented. It's got to be continuous. Although they're harder to interpret initially, most people like looking at CDFs better than histograms when making these types of choices, because there's no binning involved. If I go back to the histogram, I've been these things wrong, and I might group these two outcomes together. And then I might think there's only three outcomes. Here, I've been this thing wrong, I might get a totally different shape. But over here, there's no binning. You can always sort the data and plot it against its rank to give yourself an empirical CDF. And if you can recognize CDFs, then there's no, like, you don't have to worry that the binning is going to lead you down the wrong distribution or another. I just say there's only one CDF that corresponds to these data, and that CDF looks like an exponential CDF or something, or that CDF looks like a Poisson's CDF, or so on and so forth. Likewise here, in the stair-step version, I can learn to read that the relative height of each one of these steps is related to the probability here. So this outcome, 3, is much higher probability than this outcome, which is like 5.5, which is higher probability than this outcome, which is 6 point something. And there's an intermediate probability down here at 2. If I go back to the histogram, the heights of the histograms match what I just said there. So these histogram heights are basically the heights of these vertical steps in the sample CDF. So any questions about that? That's what I mean by sample CDFs, or looking for discrete versus continuous in a CDF. Okay. All right, so this is my kind of table borrowed from previous lectures. But I added down here a data-driven last resort. We talked about this just before the midterm. If you can't find a good distribution for some data, you can take all of your data, and the input modeling tool that you'll learn about in Lab 8 will do this for you. And you can dump it into the disk function. So you can have 1,000 data points. Well, disk can take 1,000 arguments, where basically you'll put its normalized rank, that's its sample CDF, as the odd numbered argument, and each outcome of those is the even numbered argument. And so this is a way of loading up an empirical CDF into Arena as both either a discrete version or a continuous version, and then letting Arena sample from your data itself. And so if you can't find something that's a good match, the data-driven last resort is to just say, sample from my data according to the probabilities that I actually saw in my real data. I have no idea what the model is there, but I just want to make sure that my simulation matches in probability the outcomes that I saw in the real world. And that's the way to do that with disk and quant. You can actually load up your data right into them. And again, the input modeling tool you'll learn in Lab 8, under the models menu, that's one of the options where you can choose disk or quant, and actually it will do that. Here's a data file, it will load it up, and then you can copy and paste it right into Arena, so you don't have to manually type this thing in with all of your data points. Okay. So questions about any of this? All right, so if we then just sort of exercise our physical intuition, so you should just become more comfortable. Again, this is pre-midterm stuff. Normal distribution in Arena, you implement it this way with the 2 parameters, mean and standard deviation. Sometimes they're parameterized by mean and variance, but in Arena, the second argument is standard deviation. And you have to ask, when do I use a normal? We'll have to go back and say, well, what are the interesting features of a normal? Well, it's symmetric. What's the physical basis? It is typically an additive process by the central limit theorem. Why use this distribution? Well, if you've given me a mean and a standard deviation and nothing else, and it's unbounded, this is the least unbiased distribution. So that's kind of what I've said here. So if somebody comes at you and they say, this process has an average waiting time of 20 seconds, so the standard deviation of 2 seconds, and that's all they tell you, it's just good to just choose a normal. That's the best thing for that. If they tell you it's like an average of 1 second with a standard deviation of 40, don't choose a normal, because then a lot of your outcomes will be negative. And so you're going to say, I'm going to need more information. I'm going to need to know about the skew of that distribution. Can you show me data on those waiting times? But if they don't have that data, and they've given you a mean and standard deviation which bound it way above the negative, then just use a normal. Without any other info, it's a good one to go towards. Similarly with an exponential, if they just give you a mean, then that's the good one to choose. But you have to know that it's going to give you values from 0 to infinity. It won't give you any negatives, and it'll give you potentially large values. Maybe that's good, maybe that's bad. It's also got the memoryless property. So if you're modeling the waiting time at a bus stop, it's a bad one to choose, because definitely waiting at a bus stop is not memoryless. But if you're talking about inter-arrivals at an airport, yeah, I would say that probably is memoryless, because there's, the fact that you've waited 5 seconds for the next arrival doesn't give you any information about how much more time you have to wait, because people arrive pretty much independently at the airport. So that's kind of what I'm summarizing here. If somebody gives you a mean and nothing else, except saying it's non-negative, excellent distribution to choose. It's always positive, it's memoryless, it's sort of the constant failure rate distribution, and so on. If the exponential needs kind of some adjusting to match your data, then maybe consider a Weibull. So a Weibull is like an exponential with a stretch parameter, which allows you to pull up some regions and push down some regions. And that's what that scale distribution, or that's what that shape parameter is right over there. So Weibulls you're going to have to be careful of, because this is one of those distributions, because it has more flexibility. Input modeling computer tools will tend to give you Weibulls even when exponentials are better. So if you get a tool spits out, says this looks like a Weibull, but it gives you a shape parameter that's near 1, ask yourself if it makes more physical sense for that to be an exponential. Because a Weibull with shape equal to 1 is an exponential. And you might get a more generalizable result if you choose the exponential, because it has fewer parameters. So this is kind of the so-called bias variance trade-off in building these statistical models. You want the fewest number of parameters possible to maximize generalizability. And as you add parameters, then fitting tools like Arena's input modeling or input analyzer will take advantage of them, sometimes to your detriment. And then Poisson, discrete distribution, it's a count. So if you're doing count of events, your head should go to Poisson. So, and I want to talk a little bit more about Poisson here. So, but any questions about those general outlines of those 4 distributions, the normal, the exponential, the Weibull, and the Poisson, and the different times you might use them? Okay. All right, so as you start taking data for your final project, almost definitely you're going to have to deal with inter-arrival times. And it can be, although modern tools make it easier, a real pain to measure every inter-arrival time. It's much easier to count. So rather than having someone sit there, now we have cell phones and tablets, and so every time somebody walks in, you can log it and say, there's an arrival now, and all of that can be logged, and then later you can calculate the inter-arrival time. So this advice I'm about to give is getting a little more outdated now that our data logging tools that we carry around in our own pockets are so much better. But if you find yourself like with just a pencil and a piece of paper keeping track of arrivals or whatever, it's a pain to write down times. And it's much easier to say, how many people arrived in this 10 minutes? How many people arrived in this 10 minutes? How many people arrived in this 10 minutes? And then use the count of arrivals to back out the exponential arrival rate. And that's what I'm emphasizing here, and what I'm going to show in this next example here, is that the mean number of arrivals per interval is equal to the exponential arrival rate associated with them times the interval length. So if you constantly count it, if there's an average of 10 arrivals per 10 minutes, that corresponds to an exponential arrival rate of 1 arrival per minute. So 1 arrival per minute times 10 minutes gives me my 10 arrivals per 10 minutes. So this is kind of the idea here. Poisson distribution, it takes this average number of arrivals per interval. If you look at this distribution, it's roughly where the center of mass is. So it's real easy. If you look at a Poisson distribution, you can take the average, and that's actually the best estimate of this parameter. Once you have that parameter, you can back out the exponential. So this is an example I did where I had a whole bunch of data of arrivals through a simulated process where the arrivals were roughly exponentially, interrivals are roughly exponentially distributed. And so here, what I've done is I've taken every 10-minute interval and I've counted the number of arrivals that arrive for that 10-minute interval. And I see that in some 10-minute intervals, I got as many as 70 arrivals, and others only 30 arrivals. The average was around 50 arrivals. And so if I take a histogram of the count of arrivals, this is Poisson distributed. It looks symmetric because it's got such a high average. And that's, again, just central limit theorem stuff. Things always look bell-shaped. Counts always look bell-shaped as you get high averages because of the central limit theorem. And then from this, I can easily estimate that I get a Poisson parameter of about 49.9 arrivals every 10 minutes. So I can do it that way, or I could take the exponential, I could take all of those inter-arrivals and I could then bin all of the inter-arrival times. I see there's some inter-arrivals that are always like right on top of each other, like 0. Sometimes there's as many as 60 seconds and so on. I can take these data and I can fit it, and that will give me the average inter-arrival time. And that average inter-arrival time, one over that will give me the Poisson rate, or sorry, the exponential rate of arrivals. So those are two ways I can get the exponential rate of arrivals, but they both agree. So I can go through the ugly process of recording all of the inter-arrival times, or I can just take that count data. So if I look at this from the previous slide, I estimated 49.9 arrivals per 10 minutes. Well, if I divide 49.9 by 600, where 600 is the number of seconds in 10 minutes, I get 0.08 arrivals per second. That is exactly the exponential arrival rate parameter that, if you look up here, if I try to predict the arrival rate parameter using the actual inter-arrival data, it matches this exactly. So if you've got enough counts data is much easier to get it's much easier to get exponential parameters out of Poisson count data. So like in ARENA, it's looking for the average inter-arrival time. Well, if you do 1 divided by this rate, that's going to give you the average inter-arrival time, which will be about 12 seconds. So I could either look at the average inter-arrival time from real inter-arrival data, which is a pain because you have to get every single inter-arrival duration and look at the average, and it comes out to about 12 seconds. Or I just count the number of arrivals every 10-minute interval and then average over all 10-minute intervals, and then take 1 over that, and that gives me the exact same number. So that's a much simpler way to get exponential parameters. So even though in ARENA you implement as an exponential, in the real world, you might take count data instead and do this. This saves you a lot of work. All right, so any questions about that? This shortcut where you can use the relationship between the Poisson and the exponential to connect those to reduce your data collection burden. Okay. All right, so just as this is a review, I'm not going to go through any of these, but just so you know, it's on the slide. These are a bunch of common distributions. This is how to implement them in ARENA, and here's kind of the description of them. Same thing with continuous, same thing with more continuous here, as well as this last resort, where we're using disk and cont with basically your data pairs. And then there's the input analyzer will do this for you as well. So if you can't find anything in here, you can just do a data-driven distribution. So, and then I mentioned this before, gamma and Weibel. Gamma is even worse. Gamma is basically an Erlang extended with its shape parameter to all reals rather than just integers. This is an option that the input analyzer in ARENA will fit for you. And it is so flexible that things that are Weibel, things that are exponential, they're all going to get snapped to a gamma fit. So it's going to frequently give you these gamma distributions out. And that's just because they technically will have a better fit, but they require more parameters to get that better fit, and you can overfit your data. Only choose a gamma distribution if it's clear that an exponential is a bad choice. Whenever possible, choose a good fit with fewer parameters over an excellent fit with lots of parameters. So the gamma distribution has one more parameter than the exponential. If we go to the exponential's got one parameter. The gamma distribution's got two parameters. But if that shape parameter is close to one, the gamma distribution is basically an exponential. So if you choose to fit a gamma distribution, expect questions from me about why you chose the gamma distribution over an exponential. Why wasn't an exponential a better distribution than this? And so you'd have to really sort of justify that your data are sort of not, that they are a significant deviation away from an exponential, or maybe you've got some other reason why you've chosen a gamma distribution, because ARENA doesn't know the physical basis of your data. It's just going to find the best fitting distribution. But the best fitting distribution is not always the best distribution. So if gamma pops up at the top as the best fit, look down the list. And if there's other distributions that are close to it, that have fewer parameters, maybe think about choosing those instead. So there are questions about that, this idea that you don't want to overfit your data. You're going to maximize generalization if you avoid overfitting your data. Okay, so that's all I'm sort of saying here. Be prepared to justify a gamma because an exponential or even an Erlang, like, if a gamma distribution has a shape parameter of 5.1, that could be identical to an Erlang with a shape parameter of 5. So just because it's fit this, you got a slightly better fit for your particular data, it might generalize better if you use the simpler distribution, the Erlang. Okay. So questions about any of that before we wrap up with some fat pencil test stuff? Okay, questions online? All right, so the last thing I want to cover today is probability plots, PP plots and QQ plots. So you're going to come up with guesses for these distributions, and before you go through and find the best parameters, it's good to have a tool that helps you know, did I choose a really bad guess? Like, is this just a totally different distribution? And the probability plots are ones that do that. These are fancy ways to plot your data against a hypothetical distribution, so that if you made a good choice, the resulting plot will look like a straight line that if you place a fat pencil over, you'll cover all of the data. And that would indicate a good relationship. And if you can't place a fat pencil over to cover all the data, it's probably a bad relationship. And the two probability plots that we worry about are the QQ plot and the PP plot. For both of these plots, you take your data and you sort them. This is critical. You sort all of your data so that the first data point is the lowest data point and the last sample is the highest data point. And then you do this QQ plot, which I've summarized here, but I'm going to actually then show you QQ plots and PP plots broken out. But a QQ plot basically compares the inverse CDF of your data with a hypothetical inverse CDF. And the PP plot compares the CDF of your data to the hypothetical CDF. So let's see how that works. So with a QQ plot, again, sort your data. And then you plot every data point against the inverse CDF of your hypothesis. This is the family that you think is the right family. Evaluated at the rank, the position of that point, minus 0.5, just to kind of put it in the middle, divided by the total number of data. So, if this is data point, like this might be the 5th sample in your data. So you plot that sample there, and then you do 5 minus 0.5 to get 4.5 divided by the total number of data. And that goes into the inverse CDF. And so if it's a uniform distribution, we know that the CDF of a uniform is a ramp. And so we take the inverse of a ramp and we get another ramp, and we plot that in there. So we all know how to take inverse CDFs now. You take the inverse CDF, you plug it in there, and you compare that to the actual data points. And when you do that, and this is kind of a graphical version of the KS test, sort of, then we look for a relationship. So here I've got data that was actually drawn from a normal distribution with a mean of 5 and a standard deviation of 9. And I've plotted it against a hypothetical normal, standard normal. So this hypothesis one doesn't have the right parameters at all. It has a mean of 0 and a standard deviation of 1. And yet the QQ plot shows that these points fall right on top of each other. That's the beauty of these plots, is that they, even when you don't know the parameters, they help you show that the families match up before you've even done the parameter fitting. So I've got data that has totally different parameters in the hypothesis, but I can tell that the family seems to fit. It kind of gets rid of the parameter influence, so I can just compare family of the data to family of the hypothesis. And because it's a straight line, then that's a good one. Now, instead, I could have taken data from an exponential. So let's say I sampled data that really was from an exponential, but I'm comparing it to a normal. So now I've done a QQ plot where my hypothetical distribution is a normal. So I look at the inverse CDF of a normal to get this. And this is not a line at all. This is sort of, it's far under the line on the left. It's far under the line on the right. It's kind of rising, but then slows down here. And so that tells me that I can't place a fat pencil down this line to cover it. It's a bad choice. So that's kind of the two contrasts here. And there are rules. When you look at these QQ plots, they tell you how to move towards other families. So like if all but a few points fall on the line, they're just outliers, and that family is probably good. But if the left end of the pattern is below and the right end is above, then that means that there are long tails at both ends of the data. So in other words, your hypothesis predicts data should be more in the middle, and you should try an alternative hypothesis that's more spread out. If it's the other way, left end above, right end below, then there's short tails at both ends of the data. So there's less data in the tails than expected. So your hypothetical data, it would predict less data in the tails than you're seeing in your real data. So you need to move the hypothetical one that puts more of the data toward where it is in this distribution. If I go back to this example here, where it starts low, it rises quickly, and then kind of stops rising as fast, that's this one down here, curved pattern with slope decreasing from left to right. Data is relatively skewed to the right, more extreme values on the right. That makes a lot of sense, because if I look back here, these data actually came from an exponential. That was the unknown. I tried to fit them to a normal distribution. Now we know an exponential has got a whole bunch of right skew. It has a bunch of data represented to the right of the mean. And the normal is symmetric. So this is telling me that I need a more skewed distribution than the normal, and I want something with right skew. That's what this tells me. So if I didn't know that I took the data from an exponential, as you normally won't know, then this tells me that the next family I should try should be one that gives me right skew, whereas the normal gives me no skew, and so on and so forth. And so there's these general QQ rules help you choose these families and reflect upon the choices you've already made. Now, once you've done a QQ plot, you can tune your choice using a PP plot. And this looks really similar. You sort the data just like before, but you plot a little bit differently. Now you're plotting the ranked minus 0.5, then normalized, against the CDF, not the inverse CDF, evaluated at the sample point. So if this is the 5th sample point, I'll plug in the sample here, and I'll plug in 5 here. And if this is taken from 100 data points, then n would be equal to 100. And that there compares effectively the empirical CDF against the real CDF. And I look for departures. So if I look at this example here, the histogram is a gamma distribution with parameters 10 and 5. The red line is that gamma distribution, which is the right distribution. The dashed green line is a normal distribution with a mean of 50 and a standard deviation of 15.8. On the histogram, I can't tell which hypothetical distribution is better. Now, if I look at the QQ plot, I also can't tell. The QQ plot here, the green dots or the green crosses, I guess, are the normal distribution. The red dots are the gamma distribution. They both look like they'd be covered by a fat pencil. So the QQ plot doesn't really help me discriminate. But then when I look at the PP plot, then the green line that's hanging under the line here, that is the normal distribution, whereas the red gamma that's right on the one-to-one line, that sort of follows right up against that. So that tells me that the gamma distribution is much better. So basically the way the process would go is I would use a QQ plot and it would tell me that both the gamma and the normal were an opt-in, but I couldn't tell the difference. Then I'd use the PP plot, which really compares the middle of the distributions. And this would tell me that actually, if you really look close at the middle of the distributions, the gamma is much better for these data than the normal. You should use a gamma distribution for this. And so that's kind of what I'm summarizing here. So look for lines in QQ plots, and that sort of, and then from those, that can point you from one distribution family to another. If you've got a bunch of several families that aren't discriminated by a QQ plot, then and only then you should look at them under a PP plot. And if you get also a good fit under the PP plot, then that's a good idea. That's a good evidence that that family is a good family to choose for these data. If you just look at PP plots, they're usually uninformative because PP plots, if the tails of a distribution don't match very well, the PP plots give you weird results. So the QQ plots really help you make sure the tails match first. And then once the tails are pinned down, then the PP plot helps you discriminate based on sort of the middle of that distribution. So that's why we do QQ first and then PP after that to refine our choices. All right, so any questions about that? PP plots and QQ plots and the fat pencil stuff. All right, well, I can also take questions after. Where we're going from here next time is now that we've chosen the good families, we now need to evaluate our choices. We need to choose, actually estimate those parameters that we haven't estimated yet, and then evaluate how well we did with chi-squared and KS tests. And then we'll start talking about p-values, best fits, and statistical power. So let me give you an attendance question, and then if you have any other further questions, happy to chat after. Otherwise, we'll see you on Thursday. So get my mouse back here. And the attendance question I'll give you today is, what do you do first, a QQ plot or a PP plot? Which comes first, QQ or PP in the process? And otherwise, that's all I got for you. So hope you have a good week. And those who ride the skateboard and scooter type devices, watch out. Any questions left online? If not, then I will end the meeting. Have a good day.